Hello everyone. This poster presents CoMo, a self-supervised framework for learning continuous latent motion from internet videos for scalable robot learning. I will follow the poster from left to right. First, the motivation. Discrete latent motion can mitigate the shortcut learning problem, but it leads to significant information loss and struggles to capture fine-grained dynamics. Simply removing vector quantization leads to severe shortcut learning, where the model tends to learn substantial future frame background noise as continuous latent motion. At the same time, continuous latent motion and robot action share a consistent continuous distribution, and this consistency is beneficial for unified policy learning. Next, the main contributions. We present CoMo as a self-supervised framework for learning continuous latent motion from internet videos. CoMo employs early temporal difference to enhance motion cues and increase shortcut learning difficulty. It further introduces temporal contrastive learning so that latent motion better captures meaningful foregrounds. TD and TCL work together to make the representation more precise and more action-relevant. Now let us look at the method overview in the middle. CoMo adopts an inverse dynamics encoder-forward dynamics decoder paradigm. Given the current frame and the future frame, a shared MAE pre-trained VIT extracts token-level features. CoMo then performs an early temporal difference operation to obtain temporal feature differences, and explicitly removes future frame features before the encoder extracts motion embeddings. In practice, the model uses current frame features together with the temporal differences, and a motion cue former produces the motion representation. To address the fact that sparse feature differences alone may contain irrelevant information, CoMo further proposes temporal contrastive learning. Slightly temporally offset motion pairs form positives, while reverse temporal direction forms negatives. The early temporal difference mechanism and temporal contrastive learning collaboratively mitigate the shortcut learning problem. In the experiments section, Table 2 shows results on Calvin. CoMo attains the highest performance within the autoregressive-based policy. Compared with discrete latent motion, the average score improves from 2.255 to 3.070. And using higher dimensional latent motion further improves it to 3.247. Table 3 shows results on Libero. For diffusion-based policy, CoMo achieves an average success rate of 80.1% and outperforms strong baselines such as GR00T and Dynamo. Finally, let us look at the two visual analyses on the right. Figure 3 studies motion dimension scaling. As the latent motion dimension increases, relying only on temporal difference leads to increasing action-irrelevant background noise. In contrast, adding temporal contrastive learning effectively addresses this issue and ensures the scalability of the latent motion dimension. Figure 6 is the key qualitative result. Given 2 frames from a prompt video, the model extracts latent motion and uses it to predict a subsequent frame in a new environment. The red boxes show that the naive continuous baseline incorporates static background noise from the prompt video, while CoMo avoids this issue. The yellow boxes highlight that CoMo produces more precise latent motion representations and more accurate fine-grained foreground motion. Overall, CoMo makes continuous latent motion practical for robot policy co-training by improving motion fidelity, foreground focus, and scalability. Thank you.